There are three main formulas we use when we know an object has constant or uniform acceleration. This means that the force on the object is constant in magnitude and in direction. The three formulas that we will use very often are these right here. The first two are formulas that you should be vaguely familiar with. We used them last year. But the last one is new, but it's a very useful formula. If you notice, time is not present in this formula. And so if we have situations where we don't know how much time it takes for a certain motion to occur, and we're not asked to find time, this is a very useful, quick, and efficient way to determine a value. I'd like to just show you where these three equations come from. Not everyone feels this is vital, but for some it's very important to see the origins of things. So the first formula is something we discussed earlier. It really just comes from the way acceleration is defined as the change in velocity versus time. And so v equals v sub o plus at is one that we will use very often. If we take a look at the graph that is sort of represented by this equation, look at the velocity versus time graph, we would expect to see a straight sloped line when something has constant or uniform acceleration. We'll assume for right now that the acceleration is positive just so we have something to work with, but this process works the same whether it slopes up or down. Notice that the intercept is the initial velocity and that the slope is the acceleration. So this equation follows the format we've learned in our math class of y equals b plus mx. All right, so what are we going to do with this? Well, we need to recall that for a graph of velocity versus time, the area tells us the displacement of the object, or how far the object has moved. This is because when you calculate areas, you calculate height versus a width, and so that would be a value of meters per second times a value of seconds. Seconds cancels out, and we are left with a value measured in meters. So let's take a look at this shape here, and we're going to break it into two shapes that will be easier for us to work with. So we can see a rectangle and a triangle that fit between the t-axis, the horizontal axis, and our graph. We need to represent the areas in terms of the variables up here. Let's start with the green rectangle first. So that would just be height times width, or length times width. So the height is the value of v sub o, and the width of this rectangle is the time that has gone by. So the area is v sub o times t. For the purple triangle, we'll use 1/2 base times height, where our base again is that elapsed time t, but the height is really how much the velocity has changed. The bottom of that triangle is at v sub o, and the top is at whatever that final velocity is v. So the difference between those would be our delta v, v minus v sub o. All right, so that means that our displacement during this time interval would be the sum of these two areas, so that's v sub o t plus 1/2 delta v times t. So this is starting to look like a formula we've seen before, but we certainly didn't have a delta v in there. Let's remember that acceleration is the change in velocity over time. So delta v would be a times t. We'll substitute that in and kind of see what we have left over here. Remember that displacement is how the object's position is changing, so we call that delta x. So delta x equals v sub o t plus, noticing that we have a couple of t's there, that would be a t squared divided by 2, or 1/2 a t squared. All right, well that was shown last year in class, you might remember that. How about that third formula that I said would be very useful if we did not know the time in a problem. Well, we can actually take these two equations and combine them together to derive a single equation, that new one. We're going to take the v equals v sub o equation and solve that for t. Okay, rearrange all the variables and get the t by itself. Just use a little algebra. And then here comes the messy part. We need to substitute that into the other equation. Okay, so there I've just shown you just replacing the t with that expression. But let's kind of take a look here what we have. First of all, we've got some fractions that are kind of messy. So one of the things we're going to do is to multiply everything times 2 and then also by a. And then that's going to simplify things a little bit here. We're also going to notice that acceleration can cancel a little bit. So we end up with 2a times delta x, and then we have to pick up a factor of 2 in the first term, and then one of the a's cancels with the other a in the second part, and then this is hard to explain, but hopefully you can see how the a's cancel out in the second part of that term. Let's go through a little bit more algebra here, a little bit to work our way through. We have to remember the binomial theorem, or how to use the FOIL method, and we'll distribute in the first case, and in the second case use the FOIL method or the binomial method, and we end up with a lot of terms that actually can sort of be combined. We can cancel out 2 v sub o v, and we can combine together some v sub o squareds, and we end up with this simplification. And the way this formula is usually written is like this. Okay, so v squared equals v sub o squared plus 2 times a times delta x. So these are key formulas. These will be given to you on a formula sheet that we'll use throughout the whole year. But you can certainly write those down right now so that you have them available to you as we begin some problem solving in a few days.